Kia ora. In these first few videos, we're looking through some of the preliminary material we need to approach our study of abstract algebra. In this one, we're going to take a look at the idea of equivalence. It's really useful to have a notion of equivalence that lets us take a group of objects and split them into different categories based on something they have in common. So let's dive in with our trusty Lego bricks again. So here I've got a set of bricks. They're all different in different ways. So if we're thinking about equivalence, the most fundamental thing you could have is equivalence is it's the same as equality. So for example, these two red bricks, they are equal to each other because they are the same. And we could just define equivalence to mean equality. If we do that, there's really not that much to say here because there's really not much wiggle room beyond things just being equal to each other. But instead we might want a slightly more general idea of what it means for two things to be equivalent. For example, we might say that two bricks we'll regard them as being equivalent if they have both got the same number of studs on them. So for example, these two bricks here, they both have 4 studs. So if that was our definition, then you notice that we could actually say that they're equivalent, and we can build this collection of all the bricks that are equivalent in this pile here, and then we'd have another pile of these bricks that have 8 studs each, for example. So you can see that this idea of equivalence, i.e. the number of studs, has split my set up into 2 non-overlapping subsets. Okay, so let's put them back in our set for a moment. That's not the only way we could define equivalence. We're kind of free to do what we want. Another thing we could do is we could say that 2 bricks are equivalent if they're the same color. In which case we'd have these ones being equivalent, these ones, these 3, these 2, that one as well, and the blue ones and the red ones. So in this case, it's split our set up into, this time, 6 subsets. And again, each of these sets does not overlap with the other ones, and it contains elements, each pair of which are equivalent to the other ones in that subset. So just as a sort of a preview of what we're going to do in the next video, when we take a set and split it up into things that are equivalent like this, these individual subsets are known as equivalence classes. And we can define an equivalence class, which is say these lime green ones, by taking one element, doesn't matter which one, and if we draw some square brackets around it, that just means the set of all things that are equivalent to this element. That's called the equivalence class, represented in this case by that square brick. This would be the same set as with this, but we'll cover these in more detail in the next video. The important point about these is that they actually split our set up into this, what we call a partition of non-overlapping subsets. Again, more on this next time. Right, so that's the basic idea. There are, however, a few technical details that we need to have a look at. So let's start a little bit more carefully with what's happening when we're defining equivalence. So really, if I grab 2 bricks, I'm trying to think about what it means for 2 bricks to be equivalent. I'm trying to assess them to decide if they're equivalent or not. So when I'm taking 2 bricks like this, I can treat those as an ordered pair. So let's just bring in another copy of our set so that we can work with the Cartesian product of our set S with itself. So if I want to decide whether 2 bricks are equivalent, I'm taking, for example, this yellow square and this blue rectangle, and these are like an ordered pair. And if we were using, for example, our color definition of equivalence, these 2 would not be equivalent. But if I were to say take 2 bricks that were equivalent by that definition, that would be an ordered pair. In fact, let's just get a piece of paper underneath so I can write that. This here is an ordered pair of bricks that is equivalent. So here we go. And it's a member of the Cartesian product of my set S with itself. So if you think about it, I can go through other examples. So I could find that these 2 would be equivalent. Again, I'm using the color definition of equivalence here. So what that means is if I take all of the possible ordered pairs that I regard as being equivalent, then they're going to form a subset of S times S, of the Cartesian product of S with itself. So our idea of equivalence actually gives a subset of S times S. So we'll call this thing an equivalence relation is a subset R of S times S, and consists of ordered pairs A and B, where, smooth that up, A is equivalent to B. Alright, so that's not quite a definition yet, but it's hopefully giving the idea that the way we actually define equivalence relations is we define a subset of this Cartesian product. It seems a bit backwards because it's much more natural to think of equivalence as being some kind of property that has to be in common with the two things, like how we had the idea that two things were equivalent if they were the same color or if they had the same number of studs. But actually, we define equivalence relations to be a subset of the Cartesian product. And because we're doing it that way, which feels a bit less natural, it does mean we have to impose some rules on this subset to make this actually make sense. So for example, let's just take a simpler set of Lego bricks rather than this big one. Imagine our set was just the red and blue bricks. So the set S now just has these two, and if we want to look at all of the ordered pairs, there'd be this one, there'd be this one, there'd be this one, and then there would be blue, blue. Okay, so remember that we've got this idea that an equivalence relation is a subset of this bigger set here. So let's just imagine it was this really simple subset. Imagine it was just this pair here. Move these a bit further up. So my subset is just this ordered pair blue, red. Now, is this an equivalence relation? Well, if my subset is just the pair blue, red, in fact, just put some paper under that again just to emphasize what we're doing here. So I'm just saying this is my equivalence relation here, a subset of the Cartesian product that just consists of those two bricks. And the way I read this is this tells me that blue is equivalent to red. But this whole thing doesn't really feel like an equivalence relation because, for example, the pair red-blue is not a member of this subset. So that would mean that red is not equivalent to blue, although blue is equivalent to red. Now this doesn't really match the idea of equivalence that sort of feels natural. So one thing that we're going to have to say is going to be true, that if for a subset of S times S to be an equivalence relation, it needs to make sure it contains both pairs. If you got blue-red, you need to also have red-blue, because it doesn't really make sense to say A is equivalent to B, but B is not equivalent to A. That doesn't feel like equivalence to me. Okay, so let's now state the formal definition of equivalence relations. So an equivalence relation on a set S is a set or a subset R of S times S, such that, now there are three properties that have to be true. Let's see what these are. First one is that a member of the set has to be equivalent to itself. So this first property is that X, X has to be a member of the equivalence relation for every X in S. And this is known as the reflexive property. Okay, now the second one is that one we just mentioned, which is that if I have a pair XY in my equivalence relation, this implies that I also have to have YX in my equivalence relation as well. Okay, I cannot have X is equivalent to Y without having Y as equivalent to X, and this is known as the symmetric property. And there's one third one, which is a little bit more complicated, but not too much more so, which is that if I have X and Y if X is equivalent to Y and Y is equivalent to Z, then, in fact, why don't you just pause the video and see if you can decide what that should imply before we fill in the gap. So that implies if x is equivalent to y and y is equivalent to z, that means that x must be equivalent to z also. And this is called the transitive property. Now, it's all very well to talk about subsets, and indeed this is how equivalence relations are formally defined, but it's not really how we talk about it. Okay, we don't usually, it feels a bit clunky to use this sort of subset definition of equivalence to make sense of what's happening. So what we usually do instead, we keep in the back of our minds that equivalence relations are defined in terms of Cartesian products, and awesome. What we actually normally do is we define a symbol of some sort. So for example, you might use a tilde, or like a approximately equals type sign, or maybe the 3 bars equals. And we use a symbol like that, and instead of writing that AB is a member of our equivalence relation, we write A is equivalent to B using the symbol that we've defined. So this is the same thing. Okay, so if we write the rules down that we just had, our 1, 2, and 3, using this notation, it kind of feels a bit more natural. So that would mean that in the first case, we'd have that x is equivalent to itself for all x in my set. Now that little upside down triangle A thing, that just means it's a shorthand for all. Normally I'll write the words out, but sometimes we'll just use that shorthand. Second one, the symmetric property, that one says that x is equivalent to y implies, and let's just practice using some more symbols, using arrows this time, implies that y is equivalent to x. This is for x and y in our set, which I won't bother to write down. And the third property is that x is equivalent to y and y is equivalent to z implies that x is equivalent to z. So most of the time we will actually use notation more like this for equivalence rather than using our set notation. But just once again, remember that in the background we do have this idea that equivalence relations are actually subsets of a Cartesian product. They're not defined by this symbol. So a really important example is that of congruence modulo n. So this is the idea that we can define an equivalence relation for numbers that are basically separated by some multiple of some integer n. So for example, if n was 4, then we'd have the following numbers would all be kind of congruent mod n, because they're all separated by multiples of 4. This would be with n equals 4. So let's quickly pull up the definition of congruence mod n, and then we'll use our properties of equivalence relations to show that our congruence mod n is indeed an equivalence relation. So this is going to be a really good example of showing that something specific satisfies a definition by just working through the properties kind of methodically step by step until we've established them all. So here's our formal definition. We have basically two integers r and s, and we've also got a natural number n. So notice n is not from the integers, n is from the natural numbers, so it's positive. So we say that r is congruent to s mod n, or in shorthand we use this sort of 3 equals sign. R is equivalent to s mod n if there is an integer k such that the difference between r and s is equal to k times n. So we're just looking at the difference of the numbers and seeing if that's a multiple of n. So before we had that was 4. Okay, so let's see if we can figure out let's just practice using that notation first. So for example, we had -3 and 9 before, so we can show that -3 minus 9 is equal to -12, which in turn is equal to -3 times 4. So with n equals 4, that's our n here, this is our k. So because we can write the difference between -3 and 9 as a multiple of 4, we can say that -3 is equivalent to 9 mod 4. So that's what that means. Right, so we're going to show that congruence mod n, no matter what n is, just for a fixed n, is an equivalence relation. So just a quick reminder, we've got these equivalence relation properties here, just sort of summarized. So we need to show that this operation is reflexive, symmetric, and also transitive. So we'll start with reflexive. Let's see what that means in the context of our problem. So what we need to show is that if we pick a single r from, in this case, the integers, then it has to be equivalent to itself. So we'd start off by saying something like, let r be an integer, because it has to work no matter which integer we choose, so it's coming from our base set. Then we need to show that it's equivalent to itself, so that means for the case of congruence mod n, we need to show that r minus r is equal to something times n. And you can see that r minus r, in fact let's just take that away, r minus r is just equal to 0, which in turn is equal to 0 times n. And this works. There's nothing in our definition that says that the k has to be non-zero. So this is our k, and therefore r is equivalent to itself mod n. Okay, so that was sort of our warm-up. The next thing we have to show is the symmetric property. So let's just write that down. So symmetric, this time we're going to take two integers. So this time we're going to say let r and s be integers. And the symmetric property says that if this is true, it follows that this is true. So if r is equivalent to s, then it must also be true that s is equivalent to r. So what we're going to do is we're going to assume that r is equivalent to s. Okay, that's the left-hand side of this statement here. Well, if that's the case, now we need to see what that means. Remember, if it's equivalent, we know from the definition that that means there's a k that makes that there true. So that gives us, then choose k, because we're going to make use of this k again in a minute, such that r minus s is equal to k times n. Okay, so that's what it gives us. If we assume that r is equivalent to s mod n, then that means we get given this k that we can now use, such that r minus s is equal to k times n. What we want to show is that s is also therefore equivalent to r. So that means we want to look at the opposite way around. We want to look at s minus r. So s minus r, we want to express that. Again, the goal here is to do some steps and show that that equals to something times n. So let's see if we can make that happen. Well, we know what r minus s is, so perhaps the obvious step here is to take a negative sign outside and to turn that into negative r minus s. The reason we do that is because we want to somehow make use of the information that we've got up our sleeve, which is that r minus s is equal to k times n. We've got that k. So that means that is equal to negative k times n. And that kind of fits what we've got here as well. That's going to be equal to, therefore, negative k times n. It's something times n, therefore s is equivalent to r mod n. Almost seems like it's too easy to put these steps down, but we have to be very careful in algebra to just methodically work with the information that we've got and not to sort of just say, oh, it's obviously true, without really thinking about why. So we've got one more property to do. We might just grab a new slide for for that one. It's the transitive property. So this time we're going to assume that R is equivalent to S and also that S is equivalent to T. And we're going to use that information to show that R is equivalent to T. So let's just turn over the page. Here we go again. So for our transitive property, this time we've got two things to assume. So suppose R is equivalent to S mod N, and S is equivalent to T mod N. Now, what we have to do is use the definition of congruence mod N to get these integers k that we can work with. Now, we've got two different equivalences here, so that means we've got two different integers k, we better call them two different letters, that we can pull in. So what we can say, then choose, let's just call them k and l, such that R minus S is equal to k times n, and S minus T is equal to L times n. So now we've got these two integers k and l to play with, and now we need to go back to the equivalence relation over here, and what we're trying to show is that this means that R is equivalent to T. So that means we want to say something about R minus T, and again we want to do a whole lot of steps and show that that is equal to something or other times n. If we can show that's true, then it is congruent to T and we're in business. Okay, so R minus T, well, it's maybe a little bit hard to see what to do with that, because the information that we've got is something about R minus S and something about S minus T. So what I'm going to do is I'm going to turn my expression into something that involves R minus S by basically subtracting it, and then to undo that subtraction I'll just add it back on. This is a very common mathematical pattern, is to add something on and take it back off again, or the other way around. So hopefully you can see that's exactly the same thing. I've just subtracted S and added S back on, but the nice thing about that is now we've got R minus T involved, so R minus S involved, and also S minus T. So that means we can go ahead and substitute in for the pieces. So that's got R minus S, we know that's equal to K times N. S minus T, that's equal to L times N. And remembering that we're aiming for something times N, we can take that one step further and say that's equal to K plus L all times N. And from that we can conclude that R is congruent to T mod N. And between the transitive property and the two we've already done, the reflexive and the symmetric properties, we can say therefore congruence mod N is an equivalence relation. So none of those individual steps were perhaps all that difficult. Maybe one of the tricky things that we come across when we're working on a problem like this is just figuring out what to do. So many problems that you work on will just involve taking a problem and breaking it down into individual steps, doing them one at a time, and often there'll only be one or two little bits that are actually tricky. The rest of it will be fairly methodical. But the general principle that we used here over and over again was establish our variables. So we supposed these things were true. Figure out what information that gives you. In this case, it gave us those two facts there. And then see how we can use this information to say something about what we actually want, which was pulling these two pieces in here. So this example of congruence modulo n is going to be one that's very important for us in this course, and we're going to use it time and time again. So just make sure you're very comfortable with it before you go moving on to other things. Otherwise, that's all for today. We'll see you in the next video. Ka kite anō.